rather reactive, lah, right? So an aluminum foil will be coated by its oxide, aluminum 2O3 oxide. Has your teacher ever discussed this? I can't hear you.
Yeah.
Okay, right. So this aluminum foil will be coated aluminum 2O3 oxide, and this is not conducting, non-conducting, and it doesn't help at all in your, in your, what do you call it? In your battery experiment. So since this is a coating, there are a few ways to deal with it, lah. One way is for you to sandpaper it, lah. Sandpaper is something easy to obtain. So if you sandpaper the aluminum foil rather gently, you will break the coating and you will have access to the real aluminum, which can then give you some sort of power, if that makes some sense to you.
Okay.
Right? So in case you run out of idea, that is something that you must do, right? Aluminum. And same thing with zinc. You have your own zinc. I'm a bit surprised that you can buy your own zinc.
They provided us with it.
Right. Now, zinc also have the same problem. Zinc also have a zinc oxide coating, which really doesn't help at all. It's because, again, it's also non-conducting. And what do? You sandpaper it. I mean, that's the easiest way to get rid of it. There will be other problems along the way. But zinc oxide, you just have to get rid of it. If you don't do this, you won't get much out of any material that you do. All right. So the problem is not the aluminum or the zinc, but the coating on them. Okay. This is usually what reactive metals do to themselves, I guess. I hope that makes some sense. Right. This is probably part of the technical knowledge that they expect you to kind of write down in your report and know these are the practical challenges. You never talk about this in theory, because in theory, we pretend that these two things doesn't happen. The zinc oxide doesn't happen. In reality, zinc oxide happens rather quickly in the experiment. Even if you sandpaper it off, soon enough, it will reform. And so you have the same problem. And so you got to tackle that. Again, doesn't exist in theory, so to speak. Right? Okay. Expect this problem to not go away that fast, right? It will be there with you, no matter what material you use. Okay, right. Anything else that you want to update?
So after that, we were searching on YouTube, and then we found this video to try, but it was a bit more complicated.
Do you guys want to try it? I mean, what kind of video is it?
Do I put it in here?
Sure. If you want me to see, no problem, right? Again, project discussion is totally up to you. I'm very happy to discuss it. If you want to discuss it, I'm again very happy. But it's up to you whether you want to, right? Okay, go ahead.
Can send it in the chat.
Where is chat? Okay, I'll wait for it. What happens today? You are by yourself, so it's a good time to discuss, right? How to make aluminum airbag. I'm gonna see it very quickly. Yeah, just a minute. Okay, you can say that that's air. It's you still need copper, right? So aluminum copper.
Yeah.
So you're saying that you are still interested in aluminum. So let's see what happens to the aluminum, right? So I'm just looking at the video and I'm just seeing what he does to the aluminum. He folded with the card and everything. I'm sorry, you have watched the video, right?
Yeah.
All right. Okay. So I have seen it until he fold the aluminum foil, right? And then I see him make Salt water, right?
Mm-hmm.
Okay. I don't know. I'm checking your PDF one more time. I think I finished seeing the video. Mhm. You know, okay. IPY4 coursework, right? Okay, let me check. Homemade battery. Okay, good, good. Okay, right. So when I read your project brief one more time, I don't see any restriction in, connecting more than one battery. You see in the video, he actually connect basically 10 alternating sheets, if that makes sense.
Yeah.
You're a physics student, so you know that that means he's seriesing the battery. He's basically he's basically putting 10 batteries in series to get higher voltage, of course. That's what you do. That's what happens when you series a battery. Am I making any sense?
Yeah.
So in your final product brief, challenge one, homemade battery can give EMF at least 1.2. So I suppose it does not matter how small of a voltage the individual battery is if you can always stack them together. That is basically what happened in a real battery. You can always stack them to create a higher voltage. So if you're going through that route, you're not going through the route of, I gotta get a very reactive metal and a very non-reactive metal. Kind of frees you to have more selection of material. I agree. As for the aluminum air battery that I see, I think if you follow, it will work, but I don't think the aluminum is the one giving the EMF. That's why the individual thing is how do I say very low voltage. Then you stack it up 10, you get 5 voltage, which is very nice and impressive. Okay. Why am I telling you this? Because your teacher will expect you guys to know whether it's the aluminum which is reacting or not, if that makes some sense. In your theory report, explain the principal mechanism. If you don't explain the fact that, oh, this reaction happens, that reaction happens, and the fact that aluminum does not, I'm guessing that the aluminum does not react in that video, then your teacher has a valid concern to you guys in that sense. So you have to be able to understand what you're assembling, cannot just follow video, if that makes some sense.
Yeah.
Right? Now, do you want to show me anything regarding your project? Anything else?
Not really.
Do you want to discuss anything else?
Like, do you think that this would work?
Yeah. It's the title is misleading. The aluminium and the air, I believe, is misleading because I don't think that tells what exactly happens in terms of reaction. Remember, we're a chemistry student, we want the reaction. So what's the reaction? But the aluminium helps as a conductor, so to speak. The air, but everything else that he used, the way the salt water and the way he layered the battery and everything, it's a general principle of making a battery. What he's doing is not weird science. He's doing a very normal science here, using all materials that you can get, which is part of your brief. Your project brief requires you to use everyday material, and he does use everyday material. So that's fair. Except the copper sheet. Then again, you can buy copper sheet very easily. Then again. Okay. Am I answering your question, sir? Did I answer your question?
Yeah.
So I think your work. Yes, you're saying?
Salt water between each layer. Would it like run out per se and evaporate and won't work after a while?
And that is a very important question because you're supposed to understand it as an O-level student. Let's talk about it for a while. Okay. Shall we talk about it? Okay.
Yeah.
Shall we talk about it so I'm talking about the theory now, which is one of the main things you have to get from your project. If you don't understand it, first of all, your project theory will be difficult to get marks. Secondly, that means your battery topic in O-level also not very good, which is not what we want, right? Here's the good news. The battery topic is going to be much easier than the electrolysis topic if you understand the electrolysis topic. The rest of it tends to be much more complicated than the battery. The bad news is if your electrolysis is not strong, then we discuss battery, it will be apparent in your confusion. So either one we'll know very soon today. So you're okay that we discuss battery?
Yeah.
Yeah. So I've already drawn the battery, correct or not? Yeah, I already drawn the battery here. And all the aluminum oxide, zinc oxide I mentioned, let's pretend that they don't exist, right? Let's pretend it. Okay, there you go. So I have aluminium CuCl, and this is no longer a battery. I teach you, Ria, if you put a battery, what does the battery determine? What does the battery dictate?
Like where the direction the charge goes.
Yes, the electron flow. And the electron flow determines what happened in terms of reaction. Fair enough, right? This part you will receive electron, this part will take electron, and the battery has the power to force things to happen, right? I told you about voluntary, involuntary reaction. Remember, I talked to you. Most of the reaction that you learn in electrolysis are involuntary. How did an involuntary reaction happen? Because the battery forces it to happen. I hope that makes some sense.
Yeah.
If you don't have a battery now you don't, right? Now you don't. Well, what you call a battery shouldn't have an external battery. I hope that makes sense. So how do you know that this is not supposed to be electrolysis? There is no battery. Secondly, it should be connected to something useful. For example, a light bulb is something useful. Make sense or not?
Yeah.
What does a light bulb need to work? A power source. In this case, the battery. So just to make things clear, this is now supposedly the battery. Am I confusing you?
No.
This looks very, 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 very similar to electrolysis. In fact, if you replace the light bulb with a battery, electrolysis will happen. This is no longer a battery. But I take out the battery, replace it with something useful, a light bulb, a voltmeter, or whatever. And then now, strangely speaking, we expect this whole thing to become a battery. If it is not confusing to you, good. Remember, electrolysis and battery appears extremely similar with the exception of, well, the battery on. Now, everything that happens here, because nobody is forcing them, should be voluntary. Right? So now I'll make my first prediction of what happened. Or rather, can you make the prediction of the reaction? Can you do that or not?
with like the aluminium and salt water.
I'm sorry, you're saying? I'm sorry.
But reaction between what?
That's well, no, that's the point. Can you predict what reaction happen? Can you predict if this is a setup? If you can, you understand battery. Just like electrolysis, if you can predict the reaction by looking at it, you understand. If you don't understand. Can you predict something? Take some time, but not too long. If you could predict something, maybe it's right, maybe it's wrong, please do so. Don't be too hesitant just because you think you might be wrong. It's not exam. Tell me your prediction. Okay. Now, first you have a half reaction. Do you understand? Do you agree that this is half reaction? This cannot be the full reaction. Half
Yeah.
reaction. Okay. This is a half reaction. Okay. Do you have another half reaction or you don't? Up to you. Feel free to guess, okay?
Is the salt water concentrated or
You can make it as concentrated or as dilute as you want. In this case, let's pretend that is your project map. So do you want to make it concentrated? It's kind of easy to make it concentrated if you want. Do you want?
yeah?
Okay, good. Let's make it concentrated. Remember, it's still aqueous lah. So go ahead. What do you think will happen if it is concentrated? The guy seems to make it very concentrated, right? So, let's follow. Concentrated stuff is in general good for a battery. So, okay, let's do that. Mm. You're listing the candidate, I like. Oh, you change your guess. Okay. Interesting. Okay, interesting. Okay. Have you, this is your final guess for now?
Yeah.
Okay. Now, I like your guess better than the first one. First thing first, I noticed that there's a reduction and there's an oxidation. Like this is gaining and this is clearly losing. Just now, I feel that you almost wrote two reduction now, which is not going to happen. How can both gain electron? Where's the electron gaining from? So that's the first thing that I like about your guess. Now, if I tell you you're wrong, my job is to explain why it is wrong and to try my best so that you understand why it's wrong. You don't just take it from my word that you are wrong. Do you understand, Ria?
Mhm.
Okay? You gotta want to understand. So now I say, hey, but Ria, this is wrong. This cannot happen. Okay, let me give you the first reason. First reason is this guy is happy. And the guy says, well, less happy. That's it. How do I know? I give you the very general principle. This is a covalent bond and this is an ionic substance, which means it is involved in some sort of ionic bond. When ionic becomes covalent, almost certainly somebody happy becomes somebody less happy. Is this voluntary or forced?
Voluntary.
No. How can happy become less happy be voluntary? Yeah, I hope that makes sense, right? This feels like a forced situation. Like you're moving H plus into a position or a situation that he doesn't like as much. So it is forced. If that makes some sense.
Mhm.
If something is forced, you got to be certain who is forcing it, who is doing the forcing. If nobody's doing the forcing, then it shouldn't happen. The H plus will stay H plus because he's already happy at that stage. He doesn't want to become less happy unless somebody forces him to do it. I hope that makes some sense. So I still haven't explained to you why you're wrong. I only explained that this is force. We better find who is doing the forcing. Okay, now let's check out the other reaction. This is also covalent and this is also ionic. Now, what does that mean?
It's forced.
Because happy to less happy. Apologies if I'm saying this. It feels like your teacher never teach. I apologize, but this is true. The forcing part, gotta understand. They have a very nice name for the force reaction. It's endothermic. The endothermics are usually forced because you gotta supply energy. That's the forcing part of. If that makes some sense. Just a minute. Halo, Mam. Ya, gimana? Sorry about that. So this force topic, it does exist in O-level syllabus. They just never use it well. I use it well, or rather, I try to use it to help your understanding. So if there are two force reaction, who is doing the forcing? At this point, there is nobody. If there's a battery outside, then you can say the battery is doing the forcing because that's what battery does. If there's nobody forcing, then likely this reaction will not happen. This reaction happens only in an electrolysis situation. That's why you seem familiar to what you're writing, but not going to happen here. Am I making any sense? Am I making any sense?
Oh yeah.
All right. Then, do you have another guess?
But if it's concentrated, didn't you say that the thing in the electrolyte will move?
In electrolysis, because it is being forced. Something I don't emphasize enough, lah, I must admit. But what you're writing here, hey, concentrated ma, so this guy will win, right? Okay. But this is ionic and this is covalent. I'm sorry, this is metallic, sorry, metallic. Same issue. Na would pretty much want to be Na plus, not the other way around. You do learn this from Sec 3. You do know what they prefer, correct? The Na does not like to be Na. The Na would really prefer to stay Na plus. So therefore, this is also forced. Same issue. Things like to be ions. Things don't like to be taken out of the ionic state. This sometimes happens in electrolysis because electrolysis is a matter of forcing involuntary stuff, right? Because of the existence of the battery. Am I making any sense right now?
Yeah. So
So
for
this
battery,
gas, yes,
ionic.
yes. You're saying, sorry.
So for batteries, it can be ionic to covalent or metallic.
No, I'm not saying that. I'm saying that if something is being forced, who is doing the forcing? It is possible that the other reaction is doing the forcing. It is possible. Right now, let's just say that I'm open-minded and I say that, okay, this guy is forced. So show me who is forcing it. It cannot be another external battery. So it might be the other reaction that you haven't guessed. If that makes some sense.
How does
Maybe,
the
yes,
other
yes, you're
react
saying.
force?
First thing first, it has to be voluntary.
But you said
In,
something else is forcing these reactions.
no. I'm saying that if this happens, somebody must be forcing it because it doesn't happen naturally. It doesn't happen naturally. And currently, I don't see any external battery. In an electrolysis, all this reaction can and will happen because of the external battery, the guy doing the forcing. If that makes some sense. The battery is literally forcing electron to the H plus. Pop. I don't care that you don't like it. Here's an electron. Pop. Something like that. That is basically what happened. And to another guy taking electron. I don't care that you want to hang on to it. Battery will take it forcefully. So the battery does all the forcing. Currently, we don't have an external battery. So the other guy doing the forcing might be another voluntary reaction, if that makes some sense.
Okay, yeah.
Do you have the other half reaction guess?
So is the first part of the equation just not ionic?
It's not gonna happen unless you provide the forcing, if that makes sense. So we are keeping an open mind here. Let's keep an open mind. It may happen, but I'm still waiting for the reason for it to happen. Which at this point, really must be a voluntary reaction already. Let me give you another possible option. Remember in electrolysis, I teach you, if the anode and cathodes are not inert, you got to consider the possibility that they react. You must always do that as a good student. Like, okay, these are the candidate lists. Okay, aluminum might react, Cu might react if this is electrolysis. Make sense so far? Are we okay? Sorry, yeah. Maybe. Okay, right. So because sometimes when you answer, it seems that your mic, so yeah, doesn't register. So in battery situation, it's actually the same thing. Hey, this is not inert. In fact, for most battery, you never start with graphite and platinum. You start somehow with, well, non-inert material. They are not inert. So in your mind, you must consider the possibility of them reacting. You tend to not do that. Yesterday, I feel, and right now I'm saying that for both battery and electrolysis, please consider the fact that aluminium can react or Cu can react. Make sense? Please consider that fact. Consider the possibility, sorry. Would that be okay? Now, I'm going to ask you to pretend that they react so that you can imagine the reaction. So please pretend that aluminum reacts because it's not inert. What will aluminum become in this case?
Will it react with chlorine?
You're thinking not in terms of half reaction. I mean that I guess it's fine that you want to say it reacts with chlorine, but in electrolysis and battery, you are allowed to just think in terms of half-half. So just think about what happened to aluminum. Don't care about the other half. Let's pretend we'll think about it separately. Don't worry about it. Okay, so okay, you're pretending the aluminum reacts. Well, memorization is group 3, so be careful there. Okay. Electron. Good. Now, for Cu, just as a practice, if Cu reacts, what will happen? All right. Tell me, is this forced or voluntary?
Voluntary.
Yeah, correct. Both of them are voluntary, which is good news. We really need something voluntary in our battery. We really need it because there's no external battery. I draw for you the reactivity series. I draw it like this. Do you remember that your teacher teach you displacement reaction?
Yeah.
Okay, so why am I mentioning that? Because in a displacement reaction, then Cu is here. I'm combining it with my reactivity series C4 plus and then aluminum 3 plus here. Now, would you look at that? The reaction that you draw is a reaction of aluminum dropping down, correct? From aluminum into aluminum 3 plus. The other one, it's here, Cu2 plus. The drop is there, but it's just shorter. Okay, just shorter. This is my way to, to very easily say to you, aluminum will volunteer much more than Cu. Way more. Because for some reason, aluminum is more reactive, and when aluminum becomes 3 plus, he is much happier than Cu becomes Cu2 plus. Cu is not the happiest guy. Cu2 plus is happier than Cu, but the difference between Cu2 plus and Cu is marginal. Compared to aluminum.
When it's happier?
I'm sorry, I what? Sorry?
How do you know when it's happier? Because for Cu2 plus, oh,
Very simple.
It's
Very
ionic.
simple. No, all here is ionic, ma'am. Correct, right? All is ionic, all is metallic. So the general lesson from Sec 3 is that all metals just want to be ions, correct? All metals just want to be positive ions. I'm saying that, all metals are just less happy than the ionic form. That one, sec 3 and is always true. Now, I'm telling you something more detailed. I'm telling you that Al3 plus is happier than Cu2 plus. There is a difference. I'm telling you that aluminium is less happy than Cu. I am not telling you something new for Sec 4 because Sec 4 teaches you reactivity series. As in the order matters, right? The order illustrates the reactivity. More reactive is simply less happy. It's simply like that. Why are you more reactive? Think about it. Because you want to change more. Reacting means changing what? Why would you want to change? Because you are, so to speak, less happy. So if Al is more reactive than Cu, according to what? According to experiments that form the reactivity series. They basically just test it out. They know that aluminium is just more reactive than Cu. They make an order to it. They ask you to memorize. You can use it. So aluminum is less happy than Cu. Clear so far? That's what reactivity series mean currently. So Cu is also a not so happy guy, but aluminum even worse. Am I making some sense right now?
Yeah.
Now, what I add to your knowledge is the fact that because aluminium becomes aluminum 3 plus, this whole thing is a mirror image. If you start very unhappy, so to speak, you will end up very happy. That is also true in nature. That's just how nature works. Cu is, of course, less happy than Cu2 plus. Cu2 plus is, of course, happier than Cu, but it does not beat this increase in happiness from Al to Al3 plus. It's actually way, way, way much more, so to speak. Am I again making any sense?
Yeah.
So if we are to choose, or if nature is to choose which one happened with these two, the aluminum one will win hands down. Hands down. Both volunteer, but Al volunteer even harder, if you understand what I'm saying. And since both is a reduct, both is an oxidation, both cannot happen. No, one shall win, and aluminum to aluminous shall win. Theoretically, this is sound and true. Okay. This is illustrated by how far the drop is. Now, dropping is in general an increase in happiness. So, just take it that way. Hey, we have at least a candidate of a very strong voluntary reaction. At least we have. Okay, so this one does not win. A bit sad. Okay, lose. A bit sad. Okay, maybe some other time. This way. Okay, maybe Al to Al3 plus will be the half reaction. Now you think about the other half, lo, you make a guess. Who or what shall happen?
Is it the OH one?
Well, it depends on a few things. This one is oxidation, right? Correct? It's an oxidation. So can I take it that it makes sense? It is not possible for another oxidation to happen. First of all, it must be a reduction. If that makes sense.
Yeah.
So is your OH thingy a reduction or oxidation? If you don't know, better write it down and check it out lah. But clearly, the other guy must be a reduction. Because gain and lose electron must still happen, ma. Sorry, yeah, oh, you're writing something. Yeah, go ahead. Did you realize that the Cl minus reaction will be an oxidation, right?
Yeah.
So, hey, cannot be two oxidation. Okay, well, so around here. Okay. It must be a reduction.
I'm not sure.
Come on. You're looking at the Cl minus and OH minus as an option, right? This will happen if you consider it, just like what I've written, and use oxidation. Now, if you consider the OH minus, there is no way that this is not oxidation. This shall be oxidation also. What else can a negative ion do but lose the negativity? A negative ion cannot be more negative. It also doesn't work that way. His content, he can be forced to lose its negativity. He doesn't like it, but he can at least. Now, losing negativity definitely means oxidation, losing an electron. So whether you consider Cl minus or OH minus, both will not happen because it is oxidation. Makes sense?
Yeah.
You are not doing the wrong thing. You just have to realize that, yeah, both will be oxidation no matter what. Both are negative, man. What bothers me a little bit is that you don't consider the positive ion. What can a positive ion do? A positive ion cannot be more positive. It doesn't work that way. It can lose positivity, which is to say it gains electron. Being forced to do so, unhappy, but can, and that's a reduction, man. You should consider that one, if that makes some sense.
But didn't you say both the 2H plus and Na plus ones were not correct?
You are correct. Both are possible, and I'll tell you who wins that. But at least in your mind, you gotta understand that. Okay, at least I have two reaction candidates. Okay, so a candidate right now is this guy and that guy. So far, so good.
Yeah.
Somebody will win. And now the displacement. Now the displacement. So first thing first, this one shall not win because the other guy just volunteers harder. So it doesn't, right? Okay, now, very conveniently, Na plus and H plus exists in the reactivity series. Here's your H plus, and here's your Na plus way down here. Very convenient, right? And you will be totally wrong, Ria. And it's very important for you to understand why.
Oh, wait.
Look at that. Look at that.
If you said the smaller jump wins, didn't...
Well, jump down and jump out matters a lot. What? No, me? Correct or not, Ria? Jumping down is voluntary.
Oh.
Jumping up is forced. Na plus becoming Na because Na is so reactive, so very unhappy, even worse than Alan. Yeah? The jump up requires a lot of force and it shall not win. Aluminium shall not win against it. The jump down is smaller than the jump up. I hope this makes a lot of sense to you. Very easy to evaluate.
Yeah.
Very, very easy. This shall not happen, and this will happen. And as taken as a whole, aluminium is forcing H plus to jump up, but it's okay. The jump up is still smaller than the jump down. That's okay. That will happen, and that precisely is what happened. Guarantee you. In theory, at least, in theory, when there are no complicating things called reality, like this does happen. Do you learn something? This is very important.
Yeah.
Wait. This affects more than the battery chapter. This is actually the reactivity series chapter, big chapter. If you understand this, you are good, way beyond battery. And every battery is just using that concept here, actually. Okay. So you have a theoretical reaction of your aluminum air. I don't know where the air comes from. Okay? I really don't know. At least theoretically, the aluminum is reacting. At least. If you understand this, I want you to make a new page and redraw everything, your aluminum air battery thingy with all the electrolyte, and decide who wins. I want you to do that by yourself. Okay? Once you're ready, don't take too long. You can also do that on paper, by the way. I'm sorry. You can also do that on paper if you want to make it a note. It is a good note. Okay, you can do it on Jamboard, you can do it on paper, and then you show me the paper because that will be your valuable note. No problem. Anything you want. Bigger jump down than who? Just to confirm.
Bigger jump down in reactivity series.
Then, when you say the word bigger, you have to say then. If it's a note, you gotta explain that, man. Then. Good, good. See. You keep, yeah. Then see you. The see you jump down. Good, good. Now that's a good note to yourself. It wins because correct. It also happens because in overall, the jump up is smaller than the jump down. Overall. Because you must take note, the second reaction is forced. Voluntary must be bigger than forced.
Wait. Overall, the jump up is smaller than the jump down.
Rather than writing it in English, maybe you just write down the reactivity series and it will make full sense. Maybe. But you just write down, okay, that might be something helpful in exam. I tend to ask my student to imagine it that way. English or sentence might not be your best ally here, right? Might not be.
What do you say about the overall jump?
Okay, first thing first, just illustrate the jump down. Just draw the jump down. This is not what your teacher, I've never seen teacher do this, but it makes a lot of sense. Please do so. And stop putting Na plus on top. On top, there's no ions.
Oh.
All right, so just do the jump, just draw the jump down now, right? Who is jumping down here, right? Okay. All right. And then draw the jump up and the jump down.
Because this is bigger than this.
Yeah. And that kind of makes sense visually, I guess. So drawing it helps. Jumping down provides energy, voluntary gives energy, exothermic, blah, 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 you know, that kind of thing. Jumping up endothermic requires energy. Energy required, smaller than energy given. Blah, blah, blah. It works out. Nature works that way. Nature makes sense, I suppose, something like that.
Okay.
Okay, so we end up covering quite a lot of things outside battery, or it turns out that battery just requires our reactivity series knowledge, kind of, something like that. Good note if you understand it. Now, if this is a battery question, there is one more thing to do. It is very particular because if you don't understand this, you don't understand the positive and negative of battery. So they will ask you, so if this is a battery, where is the positive and negative end of the battery? Because when you use a battery, you are very particular about the positive and negative direction. Correct or not? Insert it wrongly, at worst, at best, it doesn't work. No, at worst, something will get damaged. So the positive, negative matters. Now, watch me. This is the last battery knowledge, right? So you have all this salt water, right? Now, you have already established this, and therefore, electron will release, aluminum will release electron. Aluminum has two ways of releasing electron, here or there. That's it, Lo. There is no other way. One of them will win. One of them will not happen. Okay? So I am saying who will win, right? So electron has great difficulty entering water, if that makes sense. But electron has no difficulty at all entering the metal wire. This is also seen. It's still just a wire. So this shall not happen, and the guy on top shall happen, and that determines the polarity of the battery immediately. Making any sense? Okay, so that's the first thing in your note. You have to note that the two possibilities are there and who win, who lose because of what. The second thing, electron will now travel here and basically travel here. Correct. The electron will travel there. What will happen to the electron? The electron will go and meet the H plus. So your second reaction will happen at the Cu side. Also very important. If you think that it happens on the aluminum side, you are wrong. Like just wrong. The H plus will go meet the electron at the Cu side. If this doesn't make sense, you gotta tell me, right? Okay. These are the details that they look for in battery questions, whether O-level or the project also, because it determines where your positive and negative side of the battery. Now, so which one, Lei, is the positive and negative end of the battery? Can you tell? Here's a normal battery, right? This is what you call positive. This is what you call negative. According to physics, you have the advantage of a physics student, right? If this is the external wire. Where does the electron flow? Okay, according to physics, very interested in the conventional current. So chemistry, very interested in the electron flow. So electron flows how? The reverse, right? And for some quirk, actually conventional current does not happen at all. There is no such thing. There's only electron flow. Blah, 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 yada, yada. Who cares about that problem right now? Noting that you compare this with this, no? So where is the negative and the positive end of the battery? And that would be wrong, but why? Again, I gotta explain why, right? So here's the internal of the battery, which you don't know until now. Physics don't care about the internal part of the battery. Chemistry cares. Chemistry actually cares about the internal side. Physics cares about the external side, what you can put there. Correct or not? You can put in your, I don't know, your air cons lah, or whatever lah. You can put your resistor, you can put your LDR lah, whatever, all sorts of things lah. Physics are interested in the external side and chemists the internal side. And this is external, where you can plug in all sorts of stuff, and chemistry opens up the internal for you. Just like your project cares about the internal side of the battery. And that is why this is the negative and this is the positive. Am I making any sense?
I get
If I
the
don't,
internal part, but how you decide?
very simple. Electron flow. Electron flow. According to physics, externally, electron flows from the negative terminal to the positive area. No problem. Are there? See? Here's the external part of the battery, the part which is not the battery. This is where you plug in stuff. The electron flows like that. Yeah, then negative, positive. Finish it.
Oh, okay.
Makes sense there? They are now, complementary. Okay. Clear?
Yeah.
I'm going to backtrack all I said, and you better complete your note regarding this, whatever internal, external, positive, negative thing. Okay. Starting first with the electron flow. You gotta be able to tell how the electron will flow. Then everything will work out. When you're done, tell me. I'm supposed to show you something else. So I'm preparing for it.
Okay.
Okay, let me check first. Okay, and I hope as much as you can, you don't memorize this, you do understand it. Then if you want to memorize it, it's fine. Can I confirm there's no confusion here?
No.
All right, so now I'm checking through what I gave you yesterday to give you final understanding. What you need for a project. We are now no longer, we are beyond O-level. O-level syllabus, whatever you face in exam later, will be at this level. Okay, there are some weird variations of battery we haven't covered, but you know the basic stuff already. Now I'm giving you something for your project. Just a minute, I'm looking at it. There you go. Okay, you got that. Hi, we don't have to see oh wait, we should have. What is it? Oh, come on. There. Yeah, excellent. Copy page. Okay. Okay, this is what I gave you in your WhatsApp yesterday, a shortened form containing some numbers. I tell you, this is not in O-level syllabus. This is in JC syllabus if you wish to take H1 or H2 chem. Same thing, they will discuss this. This is very valuable as additional theory for your project. Very valuable. Okay. Now, you have already established your batteries foundation. If you make the guy's video aluminum air, theoretically, this is what happened. Theoretically, like, okay, Ken? Okay. Then look at this guy there. This guy there. There. That's your kind of your reaction. And there's your reaction also. I cannot. Can you are you seeing anything?
Yeah.
Okay, the Jambo is a bit messed up. Can we go? Okay. So remember what I said about forced and I'm sorry, not the CL. What am I talking about? It's not the CL. I am so sorry. It's the H. It's the H. Where's the H? There you go. There you go. Those are the two reactions. Now, remember what I told you about forced and voluntary. Your reaction is not this one, correct or not? Your reaction is the opposite of this one, correct? So the opposite, I write down again, just like what you're saying. 3 plus 3 electron. This will give you a weird number called positive 1.66 volt. You do not know where that happens, but the positive illustrates voluntarily. This voluntarily happened, and when this happened, it will, so to speak, donate positive 1.66 volt to your battery that you made. The reverse reaction is force. It is minus 1.66. It requires external battery at least the strength of 1.66 to force it to happen. The positive means it will voluntarily happen. The negative means it will not voluntarily happen. It will be forced. Do you understand what I'm saying?
Yeah.
Good. So we have a positive one. Obviously, this makes for a good battery. And then the second reaction, this is called standard. The standard reactions, happily, is what is happening here. Standard reaction is 0. No time to explain why it's 0, but it's conveniently set to 0. So therefore, putting the reaction here, it is 2H plus 2E becoming H2. If you reverse it, strangely speaking, it is also still 0 volt. No time to talk about it, but your theoretical battery will give you 1.66 volt, theoretically, which is very big. Make sense?
Yeah.
Because of these two reactions. Notice that the copper does not participate in the reaction. Notice that. The copper will not, nothing will happen to the copper. The copper is there just as a conductor. Notice that there is not a fluke. There's not a mistake. So you have 1.66 volt, and you will notice that the guy, now practically speaking, okay, this is theoretical. You have a number, which is in theory should be like that. You put it in your report. Your report is great. 2 marks for you. Then you do the practicals, and you realize that it's not 1.66. Rather than backing down, you are supposed to acknowledge the discrepancy and find out why. That will give you additional marks in your report. It's practical, it's project. Do you understand or not? If you cannot explain it, you acknowledge it, and that's already fine. If you acknowledge it and can explain further, more marks for you. Okay? Cannot explain, battery still work what? Still good. You're just a bit confused why it is not 1.66. Okay, and any case, you stack them together in series, physics, you'll get any voltage you want, so to speak. So it's not that it's a big problem anyway. Okay? You can still get a strong battery by stacking. Okay? Hey, Ria, maybe your mic. Are you okay, Ria?
Oh, yeah.
All right. So you bring this to your team, you explain that this is one possible theory of what happened, because you're supposed to explain in theory, right? Theoretically, this might be what happened, and you believe that you will encounter a number smaller than 1.66, and maybe you still don't know how to explain, but it is a good start.
Like 1.66 per layer of
Per layer. And that's not what and I don't expect that when I see the setup. I expect something low. 0.5 is actually rather high, I feel. Per layer, he has around 0.5. I think around like that. That's already considered very big for a practical battery. A practical battery always have a lot of problem one. Right? It doesn't conform to theory, and that's the fun part, I guess. But at least you have a theory. That's a good start.
wait, you know in the video he like used powdered graphite and like painted it. Like, is there a reason why he did it?
Hey, let's talk about the video, okay? So that I'm sure which one you're talking about. Hey, can you share it? Can you share you just point out to me, right? So because I want to know how much you understand the video. So you play the video, share your screen, and tell me which part.
Okay.
Mechanic on the
Okay, I'm
graphite onto these. I'm
okay,
going
okay.
quarter
Right,
inch to a
okay.
half-inch wide and about 1 inch longer than the playing card. I'm going to attach the strips to the paper towel with a couple bits of duct tape, making sure to leave about 1 inch of it overhanging. And remember, we made 11 strips, so set aside 11 strips for later. Alright, let's get some graphite onto these.
Okay,
I'm
okay.
going
So
to
he
mix
makes
my paint and my
the
graphite together.
the
I
graphite
don't have
powder, right?
specific
Okay.
proportions
Yeah.
for this. I just keep on adding graphite to the paint until I get a smooth, pasty mixture. Next, I apply it onto my pieces of paper towel on the same side as my copper strip. With the paint on, I now need to
Okay,
let
let's stop
these
there for
dry.
now.
Well, the cap
Your question, I believe, is why did he paint the towel with graphite? Something like that. The question is, does he do something else with the towel graphite copper thing? Correct? Like it's a copper towel graphite, right? Does he do anything with it after this? I believe he does lah. What is it?
Oh, does he put the salt water on it?
You check lah. You check. You gotta check.
so there's actually 2 separate pieces now. I also need to take my parchment paper. Again, water first.
Okay, he
First,
makes the
I'm gonna
water.
grab my bottom anode. That's the one with copper strip on it.
Okay, did nothing to the aluminum,
I'm gonna
right?
grab one of my cathodes, and I'm gonna put some electrolyte on.
There you go. He does that, isn't it? That's
Then
it.
I'm gonna lay it on top of the cathode.
Okay, so let's stop there for now.
Good to go.
Remember I said the challenge 2 is the portability of the battery, correct? A battery with a glass, what do you call it? A glass beaker, right? Glass beaker and salt water is a bit useless in practice, right? I mean, as like if your battery stays still, it's okay lah, but it's not portable, then that's not what you call portable. He's trying to make it portable. You see that he has no beaker.
Yeah.
He still has some salt water. Now, do you need more hint or you already thinking already?
Wait, is this about the graphite thing?
Again, you notice that graphite don't react, correct? At least you learn that theoretically. That's in general true. Fair enough. Graphites just don't react one.
Yeah.
Okay. So maybe I put it another way. Maybe in your, because this is, remember, this is an experimental project, you should try things. Like, for example, if you don't understand why the graphite is there, let's say the graphite bothers you, right? Then you should simply try without graphite and then record what happened. Make sense or not? Maybe it works. Maybe it works, but some problem pops up. Maybe it doesn't work at all. And that is a very good source of material for your report. It's actually not bad. It's actually good. Can I say it that way? If that makes sense? it will appear that you are experimenting something relevant and trying to put that as a report, and that will look very nice. Rather than you just following all the video and don't even understand why the graphite is there. If you don't understand, you just try. Good stuff. Would that be a fair answer for your team right now?
Yeah.
Easy to try, right? By the way, correct or not? Very easy to try. Okay. You may even try many things. Why paper towel? Why not something thicker? Or why not a plastic? You go and try all those stuff if your team wants to. If your team wants to. In the name of challenge 2 and challenge 3. Correct or not? Challenge 2 and challenge 3 talks about this. So it will give you more marks, hopefully, if you try many things and you report 5 things that I tried fail or something, and the 6th one, it works. And now I can kind of figure out why. Nice, good job, man. Something like that. We are outside the syllabus. Be playful. Be playful there. That's what the project wants, I believe. I would recommend all this if your team is not strong. Do you still think your team is, strong enough to do all this? Then you should gain experience, gain knowledge, gain marks, gain friendship, gain teamwork, and maybe gain a bit more confidence in doing higher level camp, if that is what you consider. If that makes some sense. Okay. Now, what do you want? Ask more questions, blah, blah, blah. What do you want?
For graphite.
Yeah.
One of us was thinking if we could just shave a pencil.
Can. In general, you can. It's very easy to shave a pencil. You just have a bit of trouble sticking it in. So that's why they added to a paint, because the paint kind of makes you able to apply, so to speak. So, but you know what? I'll put it this way. Look, I put it this way. He say to apply paint with graphite to a paper towel. You can do it differently. That will give you some mark, That will give you some marks. Like, for example, you can paste the copper strip into a piece of normal paper, which you simply draw your pencil on. And that's also applying graphite, if that makes some sense. Right? This shows that you are experimenting with different design. So no paper towel, but simply paper, because you can draw pencil on it. Can you shave? Sure, you should still try. You want to know whether it makes a difference or not if the graphite is important, but you better first establish that the graphite is important. If it is important, you want to try different design that you don't really know what will happen, but you are trying. Makes sense or not?
Yeah.
That should be easy enough to try with 3%. The result is very easy to measure. I think your teacher chose an experiment which is kind of friendly. So I feel that trying a lot of design should work here. Plus, it will differentiate you from other team. It's not that it's very difficult to find this video on YouTube. I hope that makes sense, right? You want to show that you are experimenting with different design. You do want it. You also want to show that you are trying to figure out what's going on. That you want to show. That will differentiate you from people who simply follow the video. I hope that makes some sense. Ask more question.
So instead of like each layer would give according to the video 0.5.
Maybe, but you can measure it quite easily. Like I said, there are all sorts of practical problems here. Giving a positive voltage already very good one, that's what I can say. Okay, hey, it works, Okay, great. You just measure. if I do this layer, are all the layers 0.5? Measure it by yourself, which is why I give you the voltmeter to overcome that practical problem. It doesn't make sense in this. The only thing that doesn't make sense in this experiment is your team doesn't, everybody doesn't have a voltmeter. Everybody should have a voltmeter. It doesn't make sense to cue the voltmeter. Where then what happened to the experiment? Nothing. I feel a bit bad for the other team, right? I disagree with that part of the. It's just silly, silly. Okay. Whatever you did with your own voltmeter, which I'm gonna send you, right? You repeat that on school, just to be fair. You should still repeat it. Okay. The pictures that you take should be the pictures using the school's voltmeter. That's for now, I think the best way. You'll get a lot from your project. I'm trying my best to make you get a lot from this project, not get a lot of marks, but a lot of knowledge along the way. The restriction on the voltmeter doesn't help. It's a bit silly, I think. Oh, by the way, the voltmeter I give you will not be as fancy as nice as the one in school. So it is beneficial for you to try the school one just to confirm. My voltmeter is of course cheaper, it's good to use the teacher's one. Okay.
Yeah.
So there's that. Questions?
Yeah, I think we're okay.
Okay. I will show you a very weird battery design, the one that they kind of likes to use in exam. It's a very weird one. Most battery design is simply changing and therefore changing the design. I'll show you one which is very weird in the remaining 4 minutes. You should at least know this, and then I guess we can call it a day for now. Okay. Please move on to the next page. Yeah, the shape itself is extremely weird. So this battery starts with 2 graphites connected to a voltmeter. Voltmeter is not battery, okay? So this is a battery. This is not electrolysis. This is not a battery. Just saying, not a battery. But he doesn't start with 2 metals, right? He starts with 2 inert stuff. This is inert graphite. This is inert. So a bit weird, okay? So again, nothing will happen to the graphite, right? Nothing will happen. Then here, you kind of put in H2 gas. And here, you kind of put in O2 gas. Okay, now I explain using the reaction. H2 to H plus 2 electron, right? Oxygen, O2 minus, 2O minus, 2O2 minus, plus 4 electron. I'm so sorry, the other way. Plus 4 electron, this is 2, something like that. Okay. Oh, sorry. Sorry, I shouldn't be writing this. Okay, I should be writing this, the reverse. Now you notice what I'm writing as the reverse of what you usually write. This reaction is reverse of what you usually write in electrolysis. Correct or not?
Yeah.
But the first guy also reverse, no? The first guy is also reversed. Usually in electrolysis, the other way happen, correct?
Mm-hmm.
Again, for the first one, easier to see, forced or voluntary.
Voluntary.
You're right, because covalent to ionic, that's a very easy way to evaluate. You also can see it from the reactivity series. This will be a jump down. Either way is fine. Hey, this is voluntary. The second one seems slightly harder. Look, I'll just bypass everything and say this is covalent and this is ionic, okay? This is very likely also voluntary. Let's just keep it there. So you have two voluntary reaction. Good stuff for a battery, really good. A battery doesn't need to have one voluntary and one force. It can be both voluntary one. Clear? It can be. It just cannot be both force, if that makes some sense. So these two voluntary reaction, one is definitely an oxidation and one definitely a reduction. So that's it already. No other requirements lah. So this definitely will happen lah. This definitely will happen. And there's a hydrogen here, and I'm not going to explain the membranes for now. The point is, this one will give the electron like that. The electron flow will be like this, if that makes sense. Because the hydrogen side of the reaction gives off electron will not enter the aqueous solution, it will enter the wire will go in here, and the oxygen side of the reaction will require electron, vice versa. You have your negative and your positive. So this is also a battery which looks different from the previous metal-based battery. Just saying for now. Okay? They will like to do this in exam. I hate this battery for a reason, but they would want to do this in exam, and later on when we practice, we'll come back to this. You don't have to worry about this for your project at all. Why? Because getting a hydrogen gas is very dangerous and very difficult. So this is not a battery that anybody should try, if that makes sense.
Yeah.
This is for O-level. Okay? Any other question?
No.
All right. Then I will see you next Thursday. Good. Is that good?
Okay.
All right then. See you, Ria. I'll
Yeah,
send you
bye.
the voltmeter. Bye.
Thank you.
Hi, Kirby. Okay, tomorrow you're going, really? Not on the Saturday, for example? No, really not. Oh, no, I understand what you're saying. I understand. No, I understand. I'll ask for more later lah. But you pack up. Don't be late for tomorrow. All right. Hey, but before you go, no, because you're tomorrow leaving. No. Before we end this conversation, do you know what caused you to be stressed? Yeah. Yeah. The paper was totally stressful. Yeah. I will imagine. Tell me about the paper first. The paper? The paper. Oh, right. I understand. So that happens in the middle of the English exam, lah, something like that. But you still managed to do the paper? Sorry. Right. It's just that it's not ideal, like, is what you're saying, right? It's just that it's not ideal. Understand. Then, oh yeah, how is it? Yeah. I Right. I think you should keep it for now, lah. You can keep your results, right? All right. Just keep the paper, like really keep it on your table, okay? Nothing else, okay? Remember, your table. I understand. Now the principal thing happens after the paper. Am I correct? If it happens before the paper, you wouldn't be able to concentrate, lah, I'm guessing. I understand. Do what you need, settle your Johor trip first, and keep me posted. Okay, Kirby? All right. Bye bye.